Okay, I think 4 o'clock, so we can start. So it's a great pleasure to welcome Professor Humchan today. Um, I'm doing the honors because Shonok could not be here due to sudden commitment. Humchand is very well known to all of us. I have known him for more than 2 decades. He was a PhD student with our colleague and friend, Professor Srianand, uh, almost 20 years back. And after he finished his PhD, he went to IAP, the Institute of Astrophysics in Paris, as a Gruber Foundation Fellow. And after his stint there, he joined ARIES as a faculty, the Aryabhatta Research Institute. And he had been in ARIES for almost a dozen years. And then he has now joined the Central University of Himachal Pradesh. He is a Dean of Physical and Chemical Sciences. He's a professor. He's the head of the Department of Physics and Astronomical Sciences. In the middle, Humchand also became a young associate of the Indian Academy of Sciences, and his research interests span a wide variety of things. He was very famous as a young student for working with Anand on constraining the fundamental constants, but after that, his interests have spanned out into more detailed studies of active galactic nuclei in all possible ways: absorption, emission, variability, etc. And today he will tell us something about probing the environment of the central regions of AGN. Humchan, please take it away.
And thanks, Kandu, for the kind introductions, and also thanks a lot for this opportunity, in fact, extracting this talk from me. So I'm really thankful to you, and I happened to postpone it many times in the beginning. So thanks for all those cooperation and everything. So good afternoon, everybody. So I think I will mute my video for some time, because then I will open it again in the end because of some fluctuation in the internet. So please let me know if I need to unmute it sometimes. So these are the students with which I have been working over the last 10 years at ARIES, and also a few have joined here as well. So there are a list of students. I'm not sure whether I will be able to show all of work little bit, but most of the work I will be sharing whatever I have done with the students. And there's a list of my collaborators. And today's talks, as Kandu says, is not going to be on variation of fundamental constant. So today I'm going to talk about proving the environment and environment of AGN and environment of AGN and environment of central region of AGNs. So basically, and this study started when I joined at ARIES, that what kind of thing we can do using smaller telescopes to probe the AGN environments, because AGNs are very important. If we understand the environment, if we understand their feedbacks, they are very important for our understanding of galaxy formations. Without including the feedback from AGN, it's very difficult to match the observations. So theory and observation has otherwise discrepancies. So first part of my talk, I will be giving, knowing that there could be mixed audience, will be focused on introduction about the AGN, and then I will define what kind of few experiments we have done to probe the environment and the central engine of AGN at different length scales. Okay, so this is the picture of AGN, what I have put here in the background slides. Okay, so I will try to convince you that how we arrive at these pictures. So let's have a look on this image. So here I have marked few position of star, which we call AGN, and what we call galaxy. Okay, you can see that star and AGN looks almost like similar as far as image is concerned, but let's have a look on the spectra. This is the spectra of a star, and it is like a black body apart from absorption from the atmosphere. And this is the spectrum of galaxy. Okay, this also we understood because galaxy is nothing collections of stars, so you can have just a composite spectra. And now just have a look on this, what I call AGN or quasars. See its spectra; it's completely different than what we have seen using from the star. So it was this difference which started this field called active galactic nucleus. What's the difference here mean? You can see it very clearly. The difference is following. For instance, star is going to be like a black body, spectrum is like a black body. But if you see AGN, it's a power law spectra. And not only power law, but in addition, there is a broad emission lines. You see here H alpha, H beta, H gamma, so on and so forth. Similarly, you can see matter lines at longer wavelength. So, and more interestingly, the width of these emission lines is very broad. It's more than 1,000 kilometers per second, unlike galaxy, for instance, which is going to be less than 1,000 kilometers per second. So this means there is something certainly different than that what we are familiar with galaxies and stars in the local universe. What you can do, you can identify these lines and see they are not actually in the place where they should be in the rest wavelength. So they are redshifted. You can just match the patterns. So once you identify the which line correspond to which elements, you can use rest wavelength and observed wavelength to get redshift. Once you get redshift, then you get distance. For instance, using cosmology, you get luminosity distance. Once you have luminosity distance or this distance, you have observed flux. You could just combine them together. You get luminosity of the source, and this turned out to be quite large, almost on an average 10 times the luminosity of an entire galaxy. Okay, so this is one thing. And now another interesting thing about this agent was the variability. You see, they vary very fantastic, very quickly they vary. Since they vary very quickly, so we can put constraint on their size, that this emission is coming from what size this emission is coming. I'm just illustrating here a very simplistic example. For instance, let's suppose you are observing this bulb which is actually lighting up, and you are getting light from this corner and from this corner as well, this shell as well. If I switch off the bulb, so you won't see the bulb getting switched off instantaneously. The difference between this front side and this other sides, which is r distance away from this front sides, is going to be r by c. So there's going to be a time scale that this flux will start going to zero. Okay, this time scale of variability is going to play a very important role to just constrain the size of the object. So when this size was constrained and this variability time scale for AGN was even found few hundreds of seconds in high energy, for example, in X-ray, etc., then this size is turned out to be very small. It can be like the sun-earth kind of distance which is there. And but imagine problem is that this small region is emitting almost equivalent to 10 galaxy. So that was a problem. It was very difficult to explain that how this huge amount of luminosity we can have from such a very powerful, very compact region. So regions are very powerful and compact. A lot of effort was put whether can nuclear fusion do it. So answer turned out to be no, because then you need to have so many, you need to also constrain not only energy, you also need to show that the width of the line is more than 1,000 kilometers per second. And it turned out that strong gravity can do it, because if you see per gram energy emitted by nuclear fusion and per gram of energy emitted if we have a falling matter into a compact object, there is almost 10 time difference. So it goes with 0.7 efficiency, it goes like 10% efficiency. So almost factor 10 difference is there. So based upon these observational constraint, it was found out that for this kind of luminosity, the central compact object, whatever we required, using falling gravitational matter falling on a compact object, is going to something like 10 to the power 8 or 10 to the power 9 solar masses. If that is the case, only then we can have this huge amount of luminosity, whatever we are seeing here. And if I just compute its, let's say, Schwarzschild radius of such a compact object whose mass is 10 to the power 8, 10 to the power 9 solar masses, the typical size turn out to be comparable to whatever we expect from this variability. And similarly, the Keplerian orbital, whatever around such a compact and high mass compact object, if I just compute orbital Keplerian orbital velocity, So we can also satisfy these constraints of velocity bit to be more than 1000 kilometers per second. This is called black hole paradigms for active galactic nuclei, and this is something which is explaining the observations. But there is one thing, even let's suppose we have black holes, and, this kind of active galactic nuclei, and if I have just a redshift of something like 0.1, 0.1 redshift will correspond to something luminosity distance, something like. And even if I have size something like 10 to 120 light days, for instance, these clouds which are giving me broad emission lines. So the typical angular size of this object, which I call active galactic nuclei, is going to be something few micro arc second. And few micro arc second structure you won't be able to resolve not with any present and future facility. So it's very, very difficult. So what we need to rely upon is basically either on temporal resolutions, or we have to take spectra and we need to, let's say, analyze the spectrum. We may have to collect huge sample with different varieties of agent and then try to extract the information, what's going to happen, what the environment, what is the kinematic and structures of agents. So this is the problem, that we cannot resolve this structure. Most of these agents are at very high distance. Now, for instance, if I just take spectra, let's have a look here in this spectra. So I have one spectra in the upper side. Okay, so it has this broad H beta emission line. These are the O3 2O3 lines, and this power law. These, let's say, for instance, here another lines. These also, let's here another elements lines. These all are broad lines. And in the denominator, just below this, I'm plotting another spectra of another source, NGC 1068. It also has these O3 lines, two O3 lines doublets, but there is also H beta lines, but H beta line is only narrow. It's not as broad as like this. So these are the kind of adding puzzles, like one spectra show both narrow as well as broad, another show only narrow. So another puzzle, for instance, here, just have a look on this spectra, okay, NGC 4151, where I'm putting my mouse. So it has emission line, but on top of emission line, there is absorption. But such absorption is not seen in commonly in other agents. For example, see AKN 120. There's no intrinsic absorption, but here there's intrinsic absorption. So this is then Jew of agent based upon this spectra. And if I just elaborate on it, for instance, there are few agents who have this kind of spectra. They don't have any emission lines. Okay, and similarly, there are linear, there are cipher, there are broad line radio galaxy, narrow line radio galaxy, cipher too. I mean, in cipher, there is some set of galaxy which we call cipher, which has both narrow and broad. There is also a galaxy which we call whatever I have just now shown, which doesn't have broad, they call cipher too. So then are we seeing different kinds of agents, or basically do we have only one kind of agent, or there is it's just effect that we might be seeing them from different angle or different orientation. So this is actually where we can try to infer the structure of agent and then go to the environment of agent. Okay, what I'm just showing here, for instance, people has done this, lot of agent has been observed. You can classify them. For instance, you just take how much is radio flux as compared to optical flux. This is called radio loudness parameter. 5 gigahertz flux at 2500 angstrom. If it's more than 10, this is called one kind of sources. If it's less than 10, this is called radio quiet kind of sources. And then we can also see, for instance, these cipher ones, which have active galactic nuclei as well as host galaxy. There is QSO, which has only active nucleus, which the host is not visible. So now we know that it's basically luminosity, that these are basically fainter end of the same population. These are basically brighter end of the same population. Similarly, this set which only have narrow lines. Similarly, this type 1 agents which has both narrow line and broad lines, and these are also another kind of peculiar feature like Blazar, BLX, and Bal QSO, and so on and so forth. So there is a scheme which unify all these. Okay, right now this unification scheme consists of there's a black holes. Around black hole there is a accretion disk, and then we have these clouds which exist, which are stable clouds, but they have a capillary motion. They are million in number, so they are responsible for these broad emission lines. And there are clouds also at much further distance above here, So these are the responsible for this emission, reprocessed emission from because of the ionizing photon, which are ionizing them based upon the continuum coming from this accretion disk. So this is called narrow line region. And this discrepancy, that why we see a few of them as narrow lines, few of them both narrow and broad, can be is argued that this is a inclination effect, that if we see from this direction we see both contribution. If we happen to see from this direction, contribution from this broad line should be hidden. So for this, there is a concept of torus has been introduced. There is a torus, also dusty torus, which actually hide this broad line region. And this here the like typical time scale. This is 10 to 100 days, this BLRR, and this is few parsecs as we go to dusty torus and NLR region. And this different, for example, this IR continuum keep coming from dusty torus, and this resonant line, broader line come from high density BLR region. Forbidden lines which we saw in the spectrum come from narrow line region where density is relatively small. So this is that orientation scheme, to be precise. So in this scheme, you see here this blazars means basically if there is radio jet. So this is this above this plane which I just draw here with the dotted line, this is for radio, explaining the different variety of radio loud sources. So they should have jet. If they have jet, and then you have relativistic plasma and magnetic field, then synchrotron radiation give you a lot of radio radiation. And if you happen to see it from there, just where these relativistic particles are moving, then you have this huge continuum boosting, and then you will get this huge continuum boosted BLA sources spectrum. And emission line will be there, but they will just like noise on top of this hugely boosted continuum, so you won't see them. So equivalent width, which we say the width of emission line in unit of continuum is going to be very small. So if you have slightly emission line, you have flat spectrum radio sources, then we have broad line radio galaxies, similarly the narrow line radio galaxies, so on and so forth. And if I just remove that from here, then I have type 1 AGNs and type 2 AGNs, and so on and so forth, equivalent. So C4 galaxies are those, C4 galaxies are those, or QSOs are those, type 1 AGNs are those, where I can see both narrow line region as well as broad line region. And if I happen to see it from this side, then this broad line region is obscured by CPR2, and that's why broad line contribution is not there. So this was the puzzle actually, which I was just now pointing out here, and we can understand it. And then these are some peculiar cases, basically special directions, which correspond to something like outflows. For instance, this is one of the pictures taken from Alvis et al. 2000 papers. So you see here that there is a possibility that there is winds coming from accretion disk in these models. And if you happen to be in this line of sight, so you might see these outflowing very high speed outflow towards you. And if that is the case, then you will see all this kind of intrinsic absorption, whatever you are seeing here. So, and they could be even more extreme than whatever I've shown here. But question is the following. Now, given these pictures, okay, since we are unable to resolve the structures of AGNs, what kind of experiment we can do, what kind of things we can do to quantify, what kind of thing we can do to quantify these put observational constraint, so that we can support some of the model and we can also refute some of the models, so that we have a clear picture about the agents. So this is where I'm going to focus today. So I'm going to take a spectra of quasars. Okay. So, and this, for example, if this is a quasar and you are seeing it here, so typical spectrum of quasar is what is shown here in the dotted red lines. And then there's a lot of absorption feature because of this interaction of photons of this quasar spectrum with the intervening materials. And then I will say that I'm not going to treat this as just as a light candle. So we are going to see that how we can probe where this quasar lies, what is its environment, what is the environment of central AGN, and what is the environment at different larger scales around it. Because given that this dot here means basically this kind of structure which we have just now discussed. Okay, now this is my experiment basically, which we were doing at ARIES using smaller telescopes and whatever archival data was available. So we can use this quasar spectrum to do different kinds of science at scale more than 10 megaparsec from the source itself. For instance, we can have intervening observer, we can have associated observers. So this part I'm just not going to discuss today. So let me go to a region 1 to 10 mpc, then I go around something like 100 pc scale, then I go to something like lights and few dozens of light days, 200 hundreds of light days. Then if time permit, I will also go to the smaller scales, typically few hours to light days, just light days, um, especially regarding X-ray emitting region, etc. if time permit. Otherwise, mainly I will focus, let's go on to these two experiment. Okay, let me go to the first experiment. Okay, so what what is my intention here is the following. Now let's suppose I have a quasars. Quasar is here. Quasar, this is a quasar emission, and let's take line alpha emission lines. Light is coming. So I want to see whether I can use this spectra, whatever I'm going to get from this quasars, to probe the environment of quasars. Okay, so I'm just running it, for example. I forgot to say give its reference. Oh yeah, it's given there. So see here what is happening as light goes. So this is the light from quasar, lights come, then line alpha observation, line beta, line alpha, line beta, line alpha, line beta, line alpha, line beta. So this region from this emission line to, as you see, so you are just hitting this as soon as you hit here. So this region, now from this region to this region, it's only line alpha absorption. And apart from this, here there is a mixing. So line alpha at low redshift and line beta at high redshift will get mixed up. So what is here basically? So whatever absorption I'm getting here, so this is only related to hydrogens, and then I can have one-to-one corresponding how much amount of absorption I saw. That will tell me the amount of hydrogen present. At what redshift I saw it, that as compared to this quasar, what is the difference between this redshift and this redshift, that will tell me distance. So I can see distance from quasar at different distances, how much hydrogen is there. So for instance, let's suppose I'm interested whether quasar reside in overdense region or not. Okay, can I use this information encoded in this spectrum to get this answer? Okay, and in addition to that, what I need actually that the IgM intergalactic medium is also ionized. That's one thing. And quasar also has ionizing photon of hydrogen. All those corrections I have to take into account. But only one thing I'm 100% sure is that from this side to region to this side, this is only Lyman alpha regions. So whatever I see here, optical depth, that's basically directly related to the number of neutral hydrogen present. So 1 to n, then whatever is the redshift, that will tell me the distance from the quasar. Okay, so these are the kind of probe we can use to constrain the environment. Okay, more precisely, I'm just putting it here. Okay, so this is the experiment. Okay, and what I'm asking is the following. So I'm going to see absorption, for instance. These absorption are from very close to quasar. These absorption are very far away from the quasar. Okay, so I'm asking that, are these absorption relatively more as compared to these absorption? So one answer, are they same or are they different? So one would immediately say that they are going to be different, because we know as we go to higher and higher redshift, there is evolution. For instance, you see here quasar spectra. Low redshift, high redshift, high redshift, high redshift, high redshift. So as you go to higher and higher redshift, these absorption are more and more dense. We know that universe was smaller, it has more density, so we will have more absorption. So what I need then, I need to know what is the amount of emitters here. Okay, so I need to get handle on that, and then I need to get a handle that what would have been the matter here if quasar was not present here. Okay, so this means I need to have a intergalactic medium, control sample of intergalactic medium to do these comparisons. If I do that, then I can tell something that whether quasar has some environment which is different than that of what it would have been if there is not quasar. So that's one thing, but there is many issue. But quasar is emitting radiations, and if it's emitting, it may ionize the material around it. So we have to do that correction as well. But emission may or may not be isotropy. It could be beamed emission as well. Okay, so we have to take care that also. But also there is advantage also that this experiment allowed to prove that as well, right? So what we want in this experiment, this is called proximity effect, by the way, very close to quasar. because of ionization, you might have smaller absorption where that hydrogen got ionized. So so there is a lot of chances that we can try to prove this environment by having comparison of this with the control sample of intergalactic medium. Okay, so this is precisely the experiment. What we do, so we want to see both sides. So what we can do, we can have a pair of quasar. Okay, this quasar and this quasar. Priyanka was one student who has done all this work for us in her thesis. So this is a quasar and this is another quasar. So I can use this quasar and this sight line of the background quasar to prove the transverse direction, and this I can use to prove the longitudinal direction. So see, now I have here one quasar whose both side I can prove, transverse as well as longitudinal. So I can ask many questions now. Is the environment in the transverse direction and longitudinal direction same? Even if let's say density environment same, is the radiation field same? Because I have now this, whatever I see here, that also depend upon the radiation pressure, whether the material has been ionized or not. So those are the kind of quite interesting questions which we can address. But what it requires, this experiment, we need very close by quasar pair. So the sample is going to be quite rare kind of samples. And we need foreground quasar in the proximity region of the background quasar. I mean, we should not actually touch this lamina beta region. So we should have to be somewhere in between here. Okay, so that because here only we have one-to-one mapping between the absorption and matter contents. Okay, so the set of things goes is as follows. We have almost 3 lakhs of sources, and then we put various constraints, redshift, angular, then remove the sight line which has, let's suppose, galaxy in between this, in here some giving absorption here, and for example some peculiar object. And then we also need to bother about very careful fitting of continuums, because continuum fitting is very difficult, and all those kind of things. And we also exclude sources which are basically physical binaries, so this separation should be at least more than 2000 kilometers per second. And we got a reasonably good sample as compared to whatever was available till now in the literature. 181 quasar pair, very close with separation less than 1.5 arc minute, at redshift more than 2.5. Now let me show the result. Okay, regarding this, whether environment here and environment here is same. Nothing has been done till now, only just transmitted flux, normalized flux has been plotted here. So this is the intergalactic medium. Okay, control sample exactly matching redshift. Okay, so flux is roughly, let's say roughly 0.8. But you see here, this is the quasar emissions. Okay, this is basically toward the observer. Okay, this is the sight line toward the observer. You see here, there is a huge amount of flux. This is, as compared to 0.8, the flux is more. Flux is more mean optical depth is less. This means there is ionization. The longitudinal direction ionized. So this means this region is ionized. This side is ionized in our samples. Okay, but you see here in the transverse direction, this is intergalactic medium. Okay, because of quasar, we expect ionization. Ionization means basically more transparent, more transmitted flux, less absorption. But here thing is opposite. Okay, in the transverse direction we see even decrement in flux. This means more absorption, excess absorption. So here there is ionization. This means here there is no ionization at all. So this is something very interesting. So, and we have now flux. This has analysis is done based on flux. We can also do same analysis using optical depth. Okay, so this is a kind of statistical study, but giving very interesting result. But now thing is the following. If I just need to convert this, if I want to get some information about my environment, so what I need to correct for the effect due to quasars. Okay, ionization correction I have to do, and that's not going to be so very easy. Why? Reason is the following. Because if you see in this region, what I call proximity regions, in this region, proximity region, in this proximity region, I have general UV background radiation ionization and also quasar ionization. In the intergalactic medium, I have only ionization due to UV backgrounds. Okay, so what I would expect then, that whatever optical depth I get near the quasar, I need to scale it up, and the scaling factor need to be 1 plus ratio of the ionization rate by quasar and IGMs. So if I just correct for it, then with this optical depth, what I got here, tau proximate, this is corrected for quasar ionizations, then this I expect, if quasar has no role, if quasar doesn't have any extra overdense region or any role to play, then this optical depth distribution should match this intergalactic medium. Okay, this was my naive expectation if there's nothing like overdensity or something like that. Okay, so this is quasar ionization, and this is quasar ionization. This is ionization by intergalactic medium. So we were fortunate to get this UV background radiation from Khare and Sheehan, 2 papers, so we could do this. But first time what we did, that was more interesting stuff, that we did this ionization correction by carefully calibrating it by taking into account the spectral resolution, okay, and signal to noise also. I'm just giving you a quick analogy. Okay, let's suppose I do a simulation, and this whatever red is here, this is basically the Lyman alpha forest in the simulations. And then I switch on the quasar, then what I got is basically this black one. But then I this region, one is proximity region, one is intergalactic medium, it has to go through the spectrograph. Then because of finite resolution of spectrograph, for example, if I just take SDSS, this black curves become this red curve become this. Then I also need to rebinning, and then I also need to SNR. So you see this kind of thing. So now you see there is a huge difference between what was originally there, what was actually we are seeing in the spectrum. But we have only this, and we need to get this information. So this need to very well calibrated. We have done it this calibration using simulations, and it turned out that this the theoretical lines, what we expect theoretically for ionization corrections, 1 plus omega corrections. But what actually we saw from the simulation, that there is a departure. This 1:1. This is cut true if lines are optically thin, for example 0.01 to 0.01 range. But if I go to 0.5 to 1 optical depth regime, there's a huge departures. So we take care of all these complications in these papers, and then correct for it, and then try to answer issue about the optical depth. Okay, ratio of optical depth in the quasar region, and if quasar would not have been there. So this is that ratio. So let's take transverse direction. So this transverse direction is by this blue here. So you see here blue, and optical depth. This is basically the longitudinal directions. This red one, and if I just do the corrections, so you see there's a huge difference in the, as expected, in the flux also. It's just simply it will just get reversed. So now if you see, if I just do correction, so what I need to do, I just need to increase the optical depth in the proximity region. So this is the longitudinal directions. So longitudinal direction optical depth, I just apply the ionization correction. So it becomes this. So it matches basically what we saw in the transverse direction. Okay, at different radial bin. But in the transverse direction, I have not applied any correction as of now. What does it mean? It means that transverse direction doesn't require any correction. Okay, ionization correction. So what does it mean? It means that is quasar emitting only toward you, not in the transverse direction? Or is there something like dusty torus which is actually absorbing the radiation in the transverse direction if quasar is emitting isotropically? Okay, so that was our conclusion. Basically, we saw that it turned out that there is a dusty torus, and most of the quasar are actually type 1 Asian, and that turned out to be also a selection effect, because SDSS, all the quasar in SDSS are detected based upon broad emission lines, and all the for example, C4 lines width was available for us. We could estimate it from the spectra, and they turn out to be type 1 Asians. So, and then we thought, okay, let's apply and try to do chi-square between these two. We apply some correction on this transverse direction as well. So chi-square keep increasing, and then we see minimum chi-square is actually when there is no correction. But if we want 3 sigma, we can get 3 sigma limit here, and 3 sigma limits tell us that we are sure at 99% confidence level that illumination in the transverse direction is less than 27%. So basically, in other words, we have actually said that this quasar has dusty torus, assuming that density field around this quasar has to be spherically symmetric. Okay, so this was one of the experiment which was at times at scales of 5 to roughly 5, 6, 7, up to around 5 to 7 megaparsec scales. This experiment goes on, and we then further extended it using very high resolution data from VLT. The 100 QSOs has been used, and even we can constrain that what is the profile of this optical depth ratios near the quasar and whatever we see median optical depth in the intergalactic medium. So it looks like an exponential profile like this. And moreover, also it is found to be luminosity dependent. High luminosity and low luminosity has slightly different kind of profiles. That high luminosity over density can extend even to larger distances. So this was the major conclusion from this experiment. Okay, these are major main highlight from this experiment at larger scale. So I'm going to now the second scales, which is at typically like 100 parsec scales. Okay. So let's see in this regard, this picture as which I have just now shown you in the early times. For instance, I said that this quasar shows intrinsic absorption. This doesn't show. And see here one more extreme version of it. Okay. So this is emission lines, and these are troughs of absorption. And if you compute this width, so they can be 20,000 up to 30,000. This width is really, really enormous. Okay. And also low ionization lines appear at low when the continuum is low. I mean, this mean variable. They have variability. You see here, this is early epoch, this next epoch, third epoch. There is a huge variability. Extreme variability is also there. So this kind of sources, this kind of analysis is going to be very important to constrain such models, whatever has been proposed theoretically, that whether these balls, these kind of absorptions are basically cocoons of matter stored in the polar axis, or there is an accretion disk kind of winds. And then we have to see what is the percentage of what is the covering area of this small wind. So do we see that fraction of that many fractions of quasar showing this kind of features? So this is going to be the motivation of the second experiment. Okay, so we studied it. So this is called broad absorption line quasar. They are something like 15 to 20% of the total populations. And this width of this broad absorption line can go 2000 to even 0.1 of C. Okay, we don't know whether it's continual flow or what is the accelerating mechanisms. So all this kind of information we can try to grab based upon this. So this is a challenging task also to some extent, because continuum fitting, etc., is very, very challenging for such balls. We started this experiment back in 2014 when IUCAA Robotic Telescope was working. So at that time, we mainly focus on X-ray weak ball quasar, because about the X-ray weakness of quasar. Most of these ball quasar are found to be X-ray weaks. But few set of quasar, ball quasar we saw that they show also X-ray emissions. So we were worrying actually, are they different as compared to general populations or not? So all this monitoring first we did using IUCAA telescopes, and we find very interesting sample. I'm just showing one, for instance. You just see here, this is two epoch spectra. Okay, one was from BOSS, another was from IGO, and you see here this component is exactly matching. Okay, this means this is intervening, but see this component, there is a shift. Not only in line shift, there is also actually change in the equivalent width, in the amount of absorptions, right? So we can see based upon delta lambda whether this cloud velocity has accelerated or whether it has deaccelerated. So two sources, very interesting sources we have found at that times, and because there were only few which you can count on fingers, so they were giving us acceleration which was quite large. Okay, so Ravi Joshi was student at that times. So we did ask many questions there. What is the acceleration or deacceleration mechanism? Is it change in radial velocity component? Is it evolution in the continuum flow? Or is it basically just some material is coming and in the line of sight and then going away, and radial velocity component is different? That's what is reflecting in this change, in the shift in the line centroid. And whether the gravitational forces are there, but we exclude that, because we can do this kind of analysis. We know the velocity, we know the black hole mass, we know typical time scales, and we can have black hole mass. If we know, we can just estimate the escape velocity, see whether escape velocity is smaller than that of the velocity of outflow or not. If it's smaller, then actually gravitational forces are not going to be that important. And it turned out to be, as far as those two sources are concerned, it's basically this radial velocity component due to probably clouds coming along the line of sights with different radial velocity inclinations as time goes on. So this experiment we have recently extended. Sapna was a student and she was working on AGN feedback. So this is one of the topics she has just, I thought, let me just flash it out. So we ask many questions that whether we have rotating accretion disk accelerate this high speed by radiative forces, or these sources are in evolution state of QS, so expelling these thick shrouds, or basically, as I just now said, basically interception with the line of sights, or they may be lying along the polar axis with relatives that nested inside it. There are different people have different models. Okay, so they could be variable because of covering fraction changes, ionization condition changes, and there could be also change in the driving force as well. So all these are the possibility, but to answer all these questions, we need some reasonably well-defined sample. We need to make a sample. So we thought, let's try to devise a stuff. For instance, you see it here that these two epochs, after zero black line, then after 1.7 year, this situation, after 0.38 years, these situations. Ball completely disappeared, then again appears. Same situation goes here. Okay, so it's very important to understand location and physical condition of such absorbing gas, because things are happening there. We need to know, is it wind, what is lifetime, what is size, what is geometry, what is the kinetic powers, and how relevant it's going to be for AGN feedbacks. Okay, so what we said, let's try to make a sample which we can be studied then for various science program later on followed up. So we use SDS 7, DR7, 12, and 14. So 7, 12, 12, 14, 7, 14. So these were the kind of pairs which we have used, and after putting various set of constraints, so we end up in making new samples of such extreme, such ball which has shown extreme variability. And typically we have mainly focused on appearing walls, that also and among appearing also we have appearing pristine wall, basically where there was almost nothing, and then actually ball appears. Other general ball, mean by definition they are basically consistent, that there is a significant change, so new ball has appeared. So but this appearing pristine was actually extreme cases. So these are the kind of tasks which we have taken in this work, and try to understand these questions which I just now posed. Okay, so now let's suppose this is a situation. Here, two epoch, no data, we have not observed anything. All archival data has been taken. All data was archival. So this is the examples of epoch 1 is blue, and epoch 2, you see there is a ball has appeared. So here ball has completely disappeared. So we want to know, for instance, what is the typical rest time scales. Okay, so these are basically um, kernel distribution estimator has been used to get these probability density functions. So we use Gaussian kernel to smooth this distribution function. So you see here, appearing balls and disappearing balls, they show some significant difference. Okay, the time scale, for instance, here is quite little larger as compared to time scale for appearings. That could be slight difference because of the redshift difference, but is shown here in the inset that if we match the redshift, okay, still there is a difference. This means actually disappearing walls has longer time scale, and appearing walls, for appearing walls transitions time scale is slightly lower. All has this some implications. So for instance, whatever is shown here, does the distributions of balls which are appearing, do they have different kind of dust contributions as compared to balls which are disappearing? So what has been used here, that just as an estimator, there is this luminosity. You use Wise color W1, W2, W3, and try to get this kind of fitting lambda to the power beta. This beta distribution are compared here. So this turn out to be almost similar for both these population. But you see here flux, for instance. If you see flux, you can fit it with the power law, lambda to the power alpha. This is basically extinction in TV. This is basically K correction. So okay, this we know as a function of redshift. This can be free parameter, this can be free parameters. So we use our ball spectra. We'll try to see what happened in the case of appearing sample, what happened in the case of disappearing samples, and see, and then try to see that what is the slope. So there is a difference between these two populations, and we can infer basically that whether slope becomes steeper or whether it becomes shallower, because this tell us basically, this also give us a probe like whether this continuum is dominated by accretion, which is actually bluer when brighter, or is it other way around. For example, in the if the continuum is dominated by jet, for example, in the polar scenario, for instance. This is also quite interesting plot. I think let's spend some minute on it. So for instance, let's suppose this is delta f by f. Okay, so you have two epoch. Okay, when ball was not there and then ball was there. In the case of appearing, disappearing case, it was a just opposite. With ball was in the epoch 1, the ball was not in the epoch 2, right? So delta f by f, this means basically whether, if I just make a distribution of that, you see it here, this dotted line for disappearing. So this means when ball disappear, it is also accompanied by brightening. Okay, and when ball appear, it is accompanied by faintness. That source becomes slightly fainter. Okay, this means there is some correlation between these two. And this is basically same thing, whatever I just now said here, but in magnitude. So sign flip here. And but also it's not actually that we also can see that the light curve based upon CRT, for instance, if you just see the RMS fluctuation in the continuum, they are almost same. So amount of variability in both these populations are same. This means there is not such bias we use using that. So this is basically just same plot here, but just see per unit time, per unit area, delta m by delta t. Since rest frame is almost not very significantly different, so these two curves are almost same. But very interesting conclusion I can draw from here is the following: when ball appear, okay, this means it appear in the when source is in the faint stage. When ball disappear, this means when source is in the brighten stage. So does it give some clue that what happened, what is actually the mechanism responsible for this appearance and disappearance? Indeed, we can draw some conclusion. For instance, then it could be linked to the change in the ionization condition, for instance. So if I do photoionization modelings of this gas, any species in different ionization states, let's say C2, C3, C4, and C5. So depending upon what is the input ionization parameter, number of ionizing photon divided by the number of neutral hydrogen. Okay, this is measure of the ionizing photon basically. So you see here, if ionization parameter changes, so curves are actually different because it depends upon ionization as well as recombination. For instance, if you take C4, these two factor, C3 can go to C4 and C4 can go to C5. Okay, so which one? So one is favoring C4, another is actually disfavoring C4. So if you have two mechanisms, one favoring, one disfavoring, so anyway you will have a peak somewhere. So this peak turn out to be here. Okay, so for instance, what I'm just now saying here that if you see disappearing ball, disappearance mean basically luminous, so source become more luminous. Okay, so this means the following, that you are somewhere here. If you are in the ball stage, if source become luminous, you might go actually below detection limit. So these fractions of carbon, which will be in carbon 4, may go to the lower side, and you will not see it go below the detection threshold. And if source become fainter, this means ionization parameter is smaller. So this C4 might actually pick up. So you might you will actually see the C4. So ball will appear. So this is what is exactly this plot showing. And if we link it with this ionization change in ionization parameters, if source become luminous or source become fainter, C4 increases. So this explains that ball has appeared, and this explains that ball might have disappeared. So this kind of conclusion can be drawn, and we then understand which model is correct, which is not correct. Once we know that this is a change in ionization, if we know the ionization condition, we can ionizing flux, then we can also determine based upon that what is the typical distance of these outflows. Okay, and we know their velocity, so then we can estimate the environment as I discussed now. So these are the kind of various kind of conclusion which we can draw, whatever just now I was discussing. Okay, so let me go very briefly. So I will explain these two experiment. So I will spend 3-4 minutes on this new experiment which we have started at Aries. Okay, probably I may not be able to complete this large sample of X-ray emitting different kind of X-ray which we have studied large sample of narrow line and broad lines to constrain the X-ray emitting regions. So I will actually that few minutes I can spend on this third one, which is actually few light days time scales. Okay. So this kind of environment we can constrain. For instance, this is a picture which I was just discussing here. This is a continuum, this is a disk, and this time scale. What I can do the following. I can take this from the spectrum, I can measure continuum. Once I measure the continuum, then I have this continuum here, and this continuum, if it vary, because I said all these quasars are variables, then there's also going to variation in this ionized gas in the broad line region, which is giving me broad lines, but after some delay. Okay, so this is one light. This is then what happened in the case of lines. So basically, I'm going to use time resolution to infer actually how far this BLR is from this place. It has very interesting direction. If you know this distance, you know width, you can even get black hole mass, a key parameter in active galactic nuclei. So time resolution is that's why very important. Although we have an ability to use spatial resolutions, but it need variability. This is called reverberational mapping. So it has very interesting consequences. For instance, yeah, so it's not actually that easy, but I'm just saying single cloud, but there are many clouds actually. There are millions of clouds around it. So then we have this isodelay surface. For instance, if tau is let's say 0.01 r by c, so this is a parabola. Okay, because parabola means basically which has a locus of point, okay, which has equal distance from the focal as well as some perpendicular lines. So basically this distance and this distance, this is going to be unique. So this parabola will give me isodelay surface. I just increase it, I just increase it, I just increase it. So basically what I'm going to get finally, this means basically from set of stuff, lots of clouds, this kind of distributions. Okay, but majority of them will give me basically this one, because most of the clouds I'm going to cover are going to contribute from this isodelay surface. So most of the luminosity will come from this, because number of cloud which will be included in this is going to be the largest one as compared to this and this, right? So in this way I can estimate R. Okay, so for instance, this is the light. This is basically, let's suppose, two spectra. One spectra of a galaxy, this source in high state, and then in the low state this is the spectra, and you take difference, then what this is left residuals here. You see here H beta lines has very, so there's a huge difference. This is a residual in H beta line. So you can see actually, and in this way you can actually make the light curve of mission lines. And anyway, you can measure, let's suppose, flux at 510 angstrom where we don't have emission and absorption. Then this is the continuum light curve, and just do the cross correlations. Once you do cross correlations, then you got this delay. So we have thought of this experiment that, okay, this is very time consuming, you need bigger telescopes, it's very costly experiment. What we can do actually is the following, that instead of taking spectra, we put a narrowband filter here. Okay, do the same exercise. So we will have narrowband filter light curve as well as broadband filter light curve. So small telescope like 1.3 meter telescope, where we can afford large amount of times, can do this all light, give you light curves for both. And then once a time you can take the optical spectra to get the FWHM, and then after V square equal to GM by R, which we will get from this light curve given by photometric reverberational mapping, will give me black hole mass. It was very interesting actually. Why we got interested in it, that if we see this black hole mass estimation, all these projects till now was done in a serial mode, one object at a time, success-oriented source selection was done, and there was no coordinated effort. We thought that people have drive this LR relationship for AGNs, but it was in a high mass regime. Who knows actually whether this extend to low mass regime or not? Okay, so these were the main motives, and we bought lots of. We use these two. This is the main targets using this 1.3 meters and 3.6 meters, and we bought lots of redshifted filters. So we have a series of filters to cover H beta line, H alpha lines. So these are redshifted filters. So it costs us a lot. So it was a DSURB project. One of my project student was working on it, and then we can have light curve for narrowband, using narrowband for the emission line and broadband for the continuum, and can do this exercise. Okay. Good thing about this redshift filter is we can do stratification. For instance, if you have continuum light curve and we have different line alpha, C4, C3, H beta. You see here, delay is different. Okay, this means this is ionization stratification. Higher ionization line respond more rapidly than low ionization respond slowly. This means they are farther away. There is ionization stratification. So all these are basically goal in this experiment. So we have used many telescope for this, and we have not only our Aries telescope was used, so we have extended this project to other telescope in other countries as well. For instance, these were the 3 robotic telescope which has been used in this project. So a lot of data has been collected, and we have a lot of expectation from this experiment. We thought that if we do carry out this experiment, we will have a data. It will be a very good contribution from the observatory. Size luminosity relationship, especially in low luminosity range, will be constrained. Low luminosity range is very important because SDSS is also doing this kind of experiment, but they are doing for high mass, so they need actually 1 week cadence or so, but long duration monitoring. We are doing just over a month, but cadence is very small, which only observatory like Aries, which has telescope, can afford. So this is experiment which is actually ongoing. So results are coming, but we are collecting the data still now. So then data can be used for black hole, galaxy, whether host, whether it's constraint, classical bulb, is there any departure, whatever relationship we will get. And we can also try to constrain AGN geometry and kinematics. Even accretion disk modeling can be done because we are going to have UV when variability monitoring data and as well. Okay, so this kind of experiment we thought is we can also do. So I have 2 more experiments left here, but because of time, I'm going to stop here. So let me just stop here that I just covered this 1 to 10 MPC range using proximity effect. And we saw there is actually overdensity, and there is also dusty torus evidences. We saw the ball. So we saw there is extreme. We made a very good sample. So, and try to understand its nature. And then also one of the experiments which I just now shown here. I will just like to stop here.
Oh, thank you. Thank you, Hum, for a wide spectrum of different experiments to probe the environment of AGNs.
Thanks a lot.
It was very nice. It's open for questions. Please please raise your Zoom hand and I will unmute you.
Okay, so now let me just open my camera.
Yes. Okay, not, yes. Anand, please go ahead.
Can you hear me, Humchan?
Yes. Hi, Anand. Yes.
Hi. Acha, can you go to the plot where you have delta F by F for emerging and this thing?
Delta F by F, right.
So this comes from where?
Delta F is basically 2 epoch we have. One epoch is epoch 2.
This is from SDSS spectrum, you mean?
This is all SDSS spectrum. We have not
Can you show me that plot? I'm a bit intrigued by that.
I have plotted it. I've shown it.
Can you display that? Okay, now it's coming.
Yes.
So you mean that in some cases you have 50% change in the flux?
Yeah.
But so this is measured at what wavelength?
1700 angstrom. Yeah, because I think that's the reason where we don't have any emission absorption lines.
Okay. So I think, so what I'm saying is that it will be good to check from both sides, because one thing I learned from SDSS community is that the spectra taken with 2 camera, in the early days, they were focusing the target in the blue camera, so that in the red camera, it need not come at the center of the fiber. So when they merge, the object will appear blue, because it is ensured that all flux will go through the blue fiber, but they don't care about the red part. But when you do the latest BOSS, it was reversed. So
Okay.
they focus it on the red side. So I would check not only this, I would check in both blue channel and red channel spectrum, just to make sure that there is no systematic thing, because that is one thing you want to make sure. Because I am sure, like, you are also worried that you are telling that I look at CRTS light curve, there is nothing changing, but you look at the flux, you say factor 2 change. Correct?
Okay, but I think what we can, for instance, do, if I take DR12 and DR14, just do remake this plot, so that problem will not be there, right?
No, I think I will suggest you very simple thing. You integrate the full. We can do whatever you want, right? You take the wavelength range same, integrate the full flux. Don't give f lambda. You give integral of f lambda d lambda between 4000 and something.
Okay.
So if this systematics is there, it will introduce large scatter.
Okay.
Okay. Because I'm not. I'm a bit surprised by this because a long time back, I think Vivek is one of the author of this paper or what?
Yeah.
See, we proposed something in his during his thesis because you are thinking in terms of photoionization, but I think you have to think more physics-wise in the sense that the central region, for example, some disk instability removes some gas and throws out. Immediately, the luminosity of the disk will go down. Right?
Okay.
You are destroying. See, integral of 4 pi r square dr t of r will be altered till that particular orbit get replenished. So whenever there is an emergence, I expect the quasar to dim. And in particular in the blue, or in particular in the red, if it happens in the blue, you can say that ejection comes from the central region. If it happens in the red, you can say that ejection comes from the outer this thing. Because this we are doing in gory detail with one of my student, Aramal. So I think I'm curious about this because we spend a lot of time about this flux calibrations and how to do it.
Okay.
I would also suggest one more thing. You can look at CRTS,
Right.
not CRTS, ZTF
Okay.
and PTF. You may have photometry taken within the night close to your spectroscopic observations.
Right.
If you are lucky, then you compare whether the spectrophotometry is correct or not, because the error in SDSS spectrophotometry is very large because the standard star is not close to the thing itself, right? So
Right.
because this is very interesting result. If you convincingly show this tells you that there is a ejection related to accretion disk
Accretion disk.
instabilities.
Right.
Where the gas comes from should alter the emission, right?
Right. Okay.
We are always simple because cloudy is there, we can run it, but I don't think that is correct. I think this is what you have to think of. And this time scale may be even interesting. When the gas is ejected, it may be highly ionized, so you will not detect it. It will take some time for the gas to move along your line of sight, cool down, so that you will start detecting them. Right. Even that is interesting. So I will be surprised if immediate connection should not be there. There should be a delayed connection. I think these things are very interesting. I may send you a paper where we see how to do this because we're just getting accepted in MNRS.
Sure.
It will appear soon. I think you will find that various instabilities, how one can probe with light curves. Right. Okay, good.
Oh yeah. In fact, we are giving all these details of all this fitting, everything in the online version of this. So okay. I think that will be nice to recheck also. Thanks, Anand.
Okay, great. Gulab, please go ahead.
Thanks, Sadhu. Hi, Hum. So nice talk.
Hi, Gulab. Yeah, sure.
Yeah. So you infer the presence of dusty torus in type 1 objects based on the lake of ionization in the longitudinal direction. So right. Is it also possible to constant the torus opening angle and then connect this to the relative population of type 1 and type 2 quasars? Because observationally we know there are a much less number of type 2 quasars.
Yeah. Yes, I think they are very less in number. So, but problem is that we don't have a lot of type 2 AGN because it's very difficult to extract type 2 AGN from this huge data set, because detection algorithm right now is biased toward type 1 AGN. I think we have done little bit constraint. We just try to translate this less than 20%. See, this 20% correspond to how much angles out of the 4 pi solid angles. So we try to put it, but I think it was not actually, we're not very much convinced, so we didn't emphasize much on this, but this certainly can be done.
Okay, thanks. Kandu, if I may ask.
Yes.
Okay. So you mentioned, you mentioned the variation in broad absorption lines.
Right.
Is this variation anyway connected with the continuum or the accretion disk emission? Maybe accretion rate is varying or something like that?
Yes, this is what the conclusion is in this sample.
Okay. All right. Thanks.
Yeah.
Okay. Any other questions for whom? Whom I got confused by just this slide itself. Maybe I will talk to Anand also later.
Okay.
How do you infer a dusty torus from this transverse thing? Then maybe you
See,
went fast.
no, actually, see what happened. See, it's very, we just imagine that the density field around the quasar will be almost symmetric, right?
Yeah, but you are going about 10, a few megaparsec away from the quasar in the transverse direction.
So, but that is fine. But what I'm saying that if somebody can just obstruct the UV ionizing photons from the central region,
Ah, okay. So that way it's indirect. Okay.
yes. So then actually it's enough for us to say that this
I
density
see. I
torus
see.
might have done it.
I was wondering how you can probe
Yes.
megaparsec away some dusty torus will
No.
not extend that way.
Just
Okay, absolutely. I didn't understand. Thanks a lot. Thank you. Any other questions for whom? Last chance to grill him. Okay, if there is no other question, thank you very much, Hum, for taking time out for this.
Thanks a lot to.
I can only clap this way.
Thanks a
For
lot.
once, you will hear sound before you see the light.
Sure. Thanks a lot.
Thanks a lot. Thank you very much.
Thank you. Bye.
Bye.